All right. Hey, everyone. Apologies, I'm a little bit late. So welcome to the final lecture of CS 229 this quarter. Or I guess to the home viewers, welcome to the season finale. So what I'd like to do today is wrap up our discussion on reinforcement learning, and then we'll conclude the class. So I think, over the last few lectures, you saw a lot of, I don't know, we saw a lot of math. So maybe as a brief interlude, here are some videos. So Stanford Autonomous Helicopter, this is a project that, I don't know, Peter Bew, Adam Coates, some former students here, now some of the machine learning greats worked on when they were PhD students here. And I think using algorithms similar to the ones you learned in this class, how do you make a helicopter fly? So just for fun, this is a video shot on top of one of the Stanford soccer fields. I was actually a cameraman that day. And zooming out the camera, see the trees planted in the sky. So anyway, it turns out this is a small radio control helicopter. It turns out that when you're very far away, you can't tell if this is a small radio control helicopter or if there's like a helicopter with people sitting in it. So there was actually this, flew this on the kind of the soccer field, the big grass field off Sand Hill Road. And it turns out across Sand Hill Road, in one of the high rises, there was an elder lady that lives in one of those apartments, and if she saw this, she would call up 911 and say, "Hey, there's a helicopter about to crash," and then the fireman would come out. So anyway, to tell them, and I think they were partly relieved, partly disappointed that there was no one for them to save. I think. And so and I think let's see. One of the things I promised to do in the debugging learning algorithms lecture was to just go over the reinforcement learning example again. So let me just do that now, but with notation that I think you now understand compared to, oh, yes.
Why did the helicopter fly upside down?
Oh, it was an aerobatic stunt. Yeah, just I don't think there's any good reason for flying a helicopter upside down. Other than that, you can. There are a lot of videos of Stanford Autonomous Helicopter flying all sorts of stunts. Go to heli.stanford.edu, heli.stanford.edu, and the Stanford Autonomous Helicopter did a lot more than flying upside down. It makes some maneuvers that look aerodynamically impossible, such as a helicopter that looks like it's tumbling, just spinning randomly, but staying in the same place in the air, right? It's called a chaos maneuver, and if you look at it, you go, wow, this helicopter was turning upside down, spinning around in every same direction, but it's just staying right there in the air and not crashing. And so there are maneuvers like that the very best human pilots in the world can fly with helicopters, and I think this was just a demonstration, I guess. And I think a lot of this work wound up influencing some of the later work on the quadcopter drones in a few research labs. And yeah, I think it was a difficult control problem, and it was one of those things you do when you're at university and want to solve one of the hardest problems around. But I want to step through with you the debugging process that we went through as we were building a helicopter like this. So when you're trying to get a helicopter to fly upside down, fly stunts, you don't want to crash too often. So step one is build a model or build a simulator of the helicopter, right? Much as you saw when we start to talk about fitted value iteration. And then choose a reward function like that. And it turns out that specifying the reward function for staying in place is not that hard. Like a quadratic function like that works okay. But if you want the helicopter to fly aggressive maneuvers, it's actually quite tricky to specify what is a good turn for a helicopter, right? And then what you do is you run a reinforcement learning algorithm to try to maximize, say, the finite horizon MDP formulation, maximize the sum of rewards over t time steps. You get a policy pi. And then whenever you do this, the first time you do this, you find that the resulting controller does much worse than the human pilot. And the question is, what do you do next, right? This is, by the way, this is almost, I think this is almost exactly the slide I showed you last time, except I cleaned up the slide using reinforcement learning notation rather than the slightly simplified notation you saw before you learned about reinforcement learning. And so the question is, and again, if you're working on the reinforcement learning problem yourself, there's a good chance you have to answer this question yourself for whatever robot or other reinforcement learning or factory automation or stock trading system or whatever it is you are trying to get to work with reinforcement learning. But do you want to improve the model, or do you want to modify the reward function, or do you want to modify the reinforcement learning algorithm? Right, and modify the reinforcement learning algorithm includes things like playing with the discretization that you're using. If you are taking a continuous state MDP and discretizing it to solve over finite state MDP formulation, or modifying the reinforcement learning algorithm includes also maybe choosing new features to use in fitted value iteration, right? But there are a lot of things you could try. Or maybe instead of using a linear function approximator, instead of fitting a linear function for fitted value iteration, maybe you want to use a bigger, deep neural network, right? But so which of these steps is the most useful thing to do? So this is the analysis of those three things. If I'll give you a second to read this, right? But if these three statements are true, then the learned controller should have flown well on the helicopter, right? And so those three sentences correspond to the three things in yellow that you could work on. Is a problem that, statement 1 is false, that the assimilator isn't good enough. It's a problem that statement 2 is false, oh, sorry, I think actually 2 and 3 are reversed. Right? But the three statements correspond to the three things in yellow. I think the 2 and 3 are in opposite order, right? Is the RL algorithm maximizing the sum of rewards? Is the reward function actually the right thing to maximize? And so here are the diagnostics you could use. To see if the helicopter simulator is accurate, well, first check if the policy flies well in simulation. If your policy flies well in simulation but not in real life, then this shows that the problem is with your simulator, and you should try to learn a better model for your helicopter, right? And if you're using a linear model, this would the matrices A and B. If ST plus 1 equals AST plus BAT, if you try getting more data, or maybe try a nonlinear model. But if you find that the problem is not your simulator, if you find that your policy is flying poorly in simulation and flying poorly in real life, right? Then this is the diagnostic I would use. So I shall show these two lines. So let's let human be the human control policy. So hire a human pilot, right? Which we did. We're fortunate to have one of the best, one of America's top, aerobatic helicopter pilots working with us, and he, using his control sticks and his radio control, can make a helicopter fly upside down, tumble, do flips, loops, rolls. So we had a very good human pilot help us fly the helicopter manually. So what you can do is test whether or not so this thing here, right? That's just a payoff of the learned policy as measured on your reward function. So check if the learned policy achieves a better or worse payoff than a human pilot can, right? And so that means, go ahead and let the learned policy fly the helicopter, and then get the human to fly the helicopter and compute the sum of rewards on the sequence of states that these two systems take the helicopter through, and just see whether the human or the learned policy achieves a higher payoff, achieves a higher sum of rewards. And if the payoff achieved by the learning algorithm is less than the payoff achieved by the human, then this shows that the learn policy is not actually maximizing the sum of rewards, right? Because whatever human is doing, he or she is doing a better job maximizing the sum of rewards than the learn policy. So this means that you should, consider working on the reinforcement learning algorithm to try to make it do a better job maximizing the sum of rewards, right? And then on the flip side, this inequality goes the other way, right? So if the payoff of the RL algorithm is greater than the payoff of the human, then what that means is that your RL algorithm is actually doing a better job maximizing the sum of rewards, but they're still flying worse. So what this tells you is that doing a really good job maximizing the sum of rewards does not correspond to how you actually want the helicopter to fly. And so that means that maybe you should work on improving the reward function, that the reward function is not capturing what's actually most important to flying a helicopter well, and then you modify the reward function, right? So in a typical workflow, hoping to describe to you what it feels like to work on a machine learning project like this. And this is a big multi-year machine learning project. But when you're working on a big, complicated machine learning project like this, the bottleneck moves around, meaning that you build a helicopter, get a human pilot to fly it, get this thing to work, then you run these diagnostics, and maybe the first time you do this, you find, wow, the simulator is really inaccurate. Then you would go and work on improving the simulator for a couple months. And then, and every now and then you come back and rerun this diagnostic, and maybe for the first 2 months of the project, you keep on saying, yep, simulator is not good enough, simulator is not good enough, simulator is not enough. After working on the simulator for a couple months, you may find that item 1 is no longer the problem. You might then find that item 3 is the problem. The simulator is now good enough, but when you run this diagnostic 2 months into the project, you might say, wow, looks like your RL algorithm is maximizing the reward function, but this is not good flying. So now I think the biggest problem for the project, or the biggest bottleneck for the project, is that the reward function is not good enough. And then you might spend, another 1 or 2 or 3 or sometimes longer months working to try to improve the reward function. And you might do that for a while, and then when the reward function is good enough, then that exposes the next problem in your system, which might be that the RL algorithm is good enough. And so the problem you should be working on actually moves around, and it's different in different phases of a project. And when you're working on this, it feels like every time you solve the current problem, that exposes the next most important problem to work on. And then you work on that, and when you solve that, then this helps you identify and expose the next most important problem to work on. And you kind of keep doing that, or you keep iterating, or keep solving problems until hopefully you get a helicopter that does what you want it to. Make sense? Okay. But I think teams that have the discipline to prioritize according to diagnostics like this tend to be much more efficient than teams that kind of go by gut feeling in terms of selecting, what to spend their time on. Okay. All right. Actually, any questions about this? Oh, sorry, say that again? Yeah, I kind of want to say yes. Let me think. Yeah, I would usually check step 1 first, and then if I think the simulator is okay, then look at steps 2 and 3. Maybe one other thing about when you work on these projects, there is some judgment involved. So I think I'm presenting these things as though it's a rigid mathematical formula that's cut and dry. This formula says now work on step 1, then this one says now work on step 3. There is more judgment involved, because when you run these diagnostics, you might say, well, it looks like the simulator's not that good, but it's kind of good, and it's a little bit ambiguous, and oh, it looks like, and so that's what it often feels like. And so a team would get together, look at the evidence from all 3 steps, and then say, well, maybe the simulator is not that good, but it's maybe good enough. But boy, the reinforcement, the reward function is really bad. Let's focus on that. So there is some, so rather than a hard and fast rule, there is some judgment needed to make these decisions. But having so when I'm leading machine learning teams, often my teams will, run these diagnostics, get together, look at the evidence, and then discuss and debate what's the best way to move forward. But I think the process of making sure you have that discussion and the debate is much better than the alternative, which is, someone just picks something kind of at random, and the team does that. Right. Yeah. All right. Cool. All right, cool. So just yeah, maybe why I have the laptop up, a little bit for fun, but a little bit because to illustrate fitted value iteration. Let me just show another reinforcement learning video. Oh, and by the way, one of the, I think if I look at the future of AI, future of machine learning, there's a lot of hype about reinforcement learning for game playing, which is fine. We all love computers playing computer games. That's a great thing, I think, or something, right? But I think that some of the most exciting applications of reinforcement learning coming down the pipe, I think, will be robotics. I think over the next few years, even though there are only a few success stories of reinforcement learning applied to robotics, there are more and more right now. One of the trends I see, when you look at the academic publications and some of the things making their way into industrial environments is I think in the next several years, just based on the stuff I see my friends in many different companies and many different industries are working on, I think there will be a rise of reinforcement learning algorithms applied to robotics. I think this will be one important area to watch out for, right? So, this is another Stanford video. This, again, just using reinforcement learning to get a robot dog to climb over obstacles like these. My friends that were less generous did not want to think of this as a robot dog. They thought it was more like a robot cockroach. But I think cockroaches don't have 4 legs, right? Cockroaches have 6 legs. Yeah, but so how do you program a robot dog like this, right, to climb over terrain? So one of the key components, this is work by Zico Coulter, now a Carnegie Mellon professor, another one of the machine learning greats, is a key part of this was value function approximation, where the dog starts on the left and it goes to get to the right, then the approximate value function kind of, I'm simplifying a little bit, right? But the approximate value function tells it, given the 3D shape of the terrain, the middle plots is a height map where the different shades tell you how tall is the terrain. But given the 3D shape of the terrain, the dog learns a value function that tells it what is the cost of putting its feet on different locations of the terrain. And it learns, among other things, not to put its feet at the edge of a cliff because then it's likely to slip off the edge of a cliff and fall over, right? And so, but hopefully this gives a visualization of what a learned value function for a very complicated function looks like. And again, the space is very high dimensional, so this is all kind of projected onto 2D space. You can visualize it, but this is what a simplified value function looks like for a robot like this. Okay. All right. So with that, let me return to the whiteboard. So, there's just one class of algorithms I want to describe to you today, which are called policy search algorithms. And sometimes policy search is also called direct policy search. And to explain what this means, so far, our approach to reinforcement learning has been to first learn or approximate the value function, approximate V star, and then use that to learn or at least hopefully approximate pi star, right? So you saw value iteration, top brief, poly iteration, but our philosophy to reinforcement learning was to estimate the value function and then use that, that equation with the argmax to figure out what is pi star. So this is an indirect way of getting at a policy because we would first try to figure out what's the value function. In direct policy search, we try to find a good policy directly. Right, hence the term direct policy search, because you go straight for trying to find a good policy without the intermediate step of finding an approximation to the value function. So let's see. I'm going to use as the most fitting example the inverted pendulum. Right, so that is that thing with a free hinge here. And let's say your actions are to accelerate left or to accelerate right. Right, and you could have stay still, accelerate, strong accelerate left, strong accelerate right. You could have more than two actions, but let's just say you have an inverted pendulum with two actions. So if you want to, I'll talk about pros and cons of direct policy search later, but if you want to apply direct policy search, you want to apply policy search, the first step is to come up with the class of policies you will entertain, or come up with the set of functions you use to approximate the policy. So again, to make an analogy, when you saw logistic regression for the first time, we kind of said that we would approximate y as a hypothesis, right, whose form was governed by this sigmoid function. And you remember in week 2, when I first described logistic regression, I kind of pulled this out of a hat, right, and said, oh, yeah, trust me, let's use the logistic function. And then later we saw this was a special case of the generalized linear model. But, we just had to write down some form for how we will predict y as a function of x. So in direct policy search, we will have to come up with a form for pi, right? So we have to just come up with a function for how we represent h. In direct policy search, we'll have to come up with a way for how we approximate the policy pi, right? And so, one thing we'll have to do is say, well, maybe the action will approximate with some policy pi, maybe parameterized by theta, and it's now a function of the states, and maybe it'll be 1 over 1 plus e to the negative theta transpose, the state vector, right? Where the state vector may be something like x dot and then the angle and the angle dot, right? If this angle is phi, and maybe add an interceptor, okay? And I switch this from theta to phi to avoid a conflict in the notation, okay? This isn't really the form of the policy we'll write. So let me make one more definition, and then I'll show you a specific form of policy you can use. But it's actually not quite this. We'll need to tweak this a little bit. So the direct policy search algorithm we'll use a stochastic policy. So this is a new definition. So stochastic policy is a function, right? Okay, so we're going to use, for the direct policy search algorithm that you see today, we're going to use stochastic policies, meaning that on every time step, the policy will tell you what's the chance you want to accelerate left versus what's the chance you want to accelerate right. And then you use a random number generator to select either left or right to accelerate on your inverted pendulum, depending on the policies, depending on the probabilities output by this policy, okay? And so here's one example. Let's see, which is you can have so, continuing with the inverted pendulum, here's one policy that might be reasonable, where you say that let's see. Um, right. So, in a state S, the chance that you take the accelerate right action is given by this sigmoid function. And the chance that in a state S, you take the accelerate left action is given by that. Okay? And here's one example for why this might be a reasonable policy. So let's say the state vector S is 1 x dot phi dot, where this angle of the inverted pendulum is the angle phi. And let's say for the sake of argument that we set the parameter of this policy, phi, to be 0, 0, 0, 1, 0. So in this case, this is saying that, let's see, so theta transpose S is just equal to phi, right? And so in this case, right, because theta transpose S is just 1 times phi, everything else gets multiplied by 0. And so in this case, it's saying that the chance you accelerate to the right is equal to 1 over 1 plus e to the negative. How far is the pole tilted over to the right? And so this policy gives you the effect that the further the pole is tilted to the right, the more aggressively you want to accelerate to the right. Okay? So this is a very simple policy. It's not a great policy, but it's not a totally unreasonable policy, which is, well, look at how far the pole is tilted to the left or the right, apply a sigmoid function, and then accelerate to the left or right, depending on how far it's tilted to the right. Now, and because this is the, right, so this is really the chance of taking the accelerate right action as a function of the pole angle pi, right? Now, this is not the best policy because it ignores all the features other than phi. But if you were to set theta equals, 0, negative 0.5, 0, 1, 0, then this policy, the negative 0.5 now multiplies into the x position, right? Now this new policy, if you have this value of theta, it takes into account how far is your cot already to the right, where I guess this is the x distance, right? And the further your cot is already, I guess if your cot is on a set of rails, right, it's on a set of railway track, and you don't want to fall off and you want to keep the cot kind of centered, you don't want to fall off the end of your table. But this now says the further this is to the right already, well, the less likely you should be to accelerate to the right. Okay? And so maybe this is a slightly better policy than with this setting of parameters. And more generally, what you would like is to come up with 5 numbers that tells you how to trade off how much you should accelerate to the right based on the position, velocity, angle, and angular velocity of the current state of the cot, of the inverted pendulum. And what a direct policy search algorithm will do is help you come up with a set of numbers that results in hopefully a reasonable policy for controlling the inverted pendulum. In a policy that hopefully result in an appropriate set of probabilities that cause it to accelerate to the right whenever it's good to do so and accelerate to the left, more often when it's good to do so. Okay? So, so our goal is to find parameters theta so that when we execute pi of SA, we maximize, max over theta, the expected value of R of S0, A0 plus dot, 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 plus okay. And so the reward function could be -1 whenever the inverted pendulum falls over, and 0 whenever it stays up, or whatever, or something that measures how well your inverted pendulum is doing. But the goal of a direct policy search algorithm is to choose a set of parameters theta so that when you execute the policy, you maximize your expected payoff. And I'm going to use the finite horizon setting for the algorithm that we'll talk about today. Okay? And then one other difference between policy search compared to estimating the value function is that in direct policy search, here S0 is a fixed initial state. Okay? It turns out that when we were estimating the value function V star, you found the best possible policy for starting from any state, right? And it's kind of no matter what state you start from, it's simultaneously the best possible policy for all states. In direct policy search, we assume that either there's a fixed start state, fixed initial state S0, or there's a fixed distribution over initial states. I'm going to try to maximize the expected reward with respect to your initial state, or with respect to an initial probability distribution over what is the initial state. Okay? So that's one other difference. So, let me think how to do this. Yeah, all right. So, let's write this out. The goal is to maximize overall theta, the expected value of R of S0, A0, plus R of S1, A1, plus dot, 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 up to R of ST, AT, right? Given pi theta. And in order to simplify the math we'll write on this board today, I'm just going to set t equals 1 to simplify the math in order to not carry such a long summation. But it turns out that, so I'm just do like a 2 times step MDP just to simplify the derivation, but everything works, just with a longer sum if you have a more general version of t. Okay? And so this term here, the expectation is equal to sum over all possible state action sequences, right? And again, this would go up to ST and AT, but I'm going to set capital T equals 1, of what's the chance your MDP starts out in some state S0, so this is your initial state distribution, times the chance that in that state, you take the first action A0. Oh, actually, sorry. Yeah, let me write this out. Right, so it's the chance of your MDP going through the state action sequence, right, times that, right? So that's what it means to sort of compute the expected value of the payoff. And so instead of writing out this sum, I'm just going to call this the payoff. Right? And so this is equal to sum over S0, A0, S1, A1 of the chance your MDP starts in state 0 times the chance that in state 0 you end up choosing the action A0 times the chance governed by the state transition probabilities that you end up in state S1 times the chance that in state S1 you end up choosing S1 and then times the payoff. Okay? And so what we're going to be able to do is derive a gradient ascent algorithm, actually a stochastic gradient ascent algorithm, as a function of theta to maximize this thing, to maximize the expected value of this thing. And that and this is how we'll do direct policy search. Okay? So let me just write out the algorithm, and then we'll go through why the algorithm that I write down is maximizing this expected payoff. So this algorithm is called the reinforced algorithm. The original reinforced algorithm had a few other bells and whistles, but I'm going to explain the core of the idea. But the reinforced algorithm does the following, which is you're going to run your MDP, right, and just run it for a trajectory of t time steps. So again, I'm just gonna, well, right, and actually you would, right, technically you would run it for t time steps, but let's just say for now we'll do only the thing in blue. We run it for one time step because we set capital T equal 1. And then you would compute the payoff, right, equals R of S0 plus R of S1. And again, in the more general case, plus dot 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 plus R of ST, right? And then you perform the following update, which is theta gets updated as theta plus the learning rate alpha times and then times the payoff, right? And again, I'm just setting capital T equals 1. If capital T was bigger, you would just sum this all the way up to time t, okay? So that's the algorithm. That on every iteration through the reinforced algorithm, through the reinforced algorithm, you will take your robot, take your inverted pendulum, run it through t time steps, executing your current policy. So choose actions randomly according to the current stochastic policy using the current values of the parameters theta. Compute the total sum of rewards you receive, that's called the payoff, and then update theta using this funny formula. Right? Now, on every iteration of this algorithm, you're going to update theta. And it turns out that reinforce is a stochastic gradient ascent algorithm. And you remember when we talked about linear regression, right? You saw me draw pictures like this. If this is a global minimum, then gradient descent would just take a straight path to the minimum, but stochastic gradient descent would take a more random path, right, toward the minimum, and it kind of oscillates around there. Maybe doesn't quite converge unless you slowly decrease the learning rate alpha. So this is what we have for stochastic gradient descent for linear regression. What we'll see in a minute is that reinforce is a stochastic gradient ascent algorithm, meaning that each of these updates is random because it depends on what was this state action sequence that you just saw and what was the payoff that you just saw. But what we'll be able to show is that on expectation, the average update, this update to theta, this thing you're adding to theta, that on average, let's see, so that on average, this update here is exactly in the direction of the gradient. So that on average, because every loop, every time through this loop, you're making a random update to theta, and it's random and noisy because it depends on this random state sequence, right? This state sequence is random because of the state transition probabilities and also because of the fact that you're choosing actions randomly. But the expected value of this update, you'll see in a little bit, turns out to be exactly the direction of the gradient, which is why this reinforced algorithm is a gradient ascent algorithm. So let's show that now. Okay. So All right. So what we want to do is maximize the expected payoff, which is a formula we derive up there. And so we're going to want to take derivatives with respect to theta of the expected payoff. Right? I'm just going to copy that formula up there. Okay? So there's a chance of that going through that state action sequence times the payoff. And so we want to take derivatives of this and so we can go uphill using gradient ascent. So we're going to do this in 4 steps. Now, first, I want to remind you, when you take the derivative of a product of 3 things, right? So let's say that you have 3 functions: f of theta times g of theta times h of theta. So by the product rule of derivatives, product rule from calculus, the derivative of the product of 3 things is obtained by taking the derivatives of each of them one at a time, right? So this is f prime times g times h plus g prime here plus h prime. Okay? So the product rule from calculus is that if you want to take derivatives of a product of 3 things, then you kind of take the derivatives one at a time and you end up with 3 sums, right? And so we're going to apply the product rule to this, where we have here, we have 2 different terms that depend on theta. And so when we take the derivative of this thing with respect to theta, we're going to have 2 terms that correspond to taking the derivative of this ones and taking the derivative of that ones, right? And so this derivative is equal to, so the first term is the sum over all the state action sequences P of S0. And then, let's see. So now we'll have pi of theta, the derivative with respect to pi theta S0, A0. Right. And then plus and then times the payoff. Right, so the whole thing here is then multiplied by the payoff. Okay, so we just applied the product rule for calculus, where for the first term in the sum, we kind of took the derivative of this first thing, and then for the second term in the sum, we took the derivative of this second thing. Okay, and now I'm going to make one more algebraic trick, which is I'm going to multiply and divide by that same term, and then multiply and divide by the same thing here. Right? So lots of multiply and divide by the same thing, right? And then finally, if you factor out, so now the final step is I'm going to factor out these terms I'm underlining, right? Because this term that I underlined, this is just, the probability of the whole state sequence. Right? And again, for the orange thing, this orange thing, right? These two orange things multiplied together is equal to that orange thing in that box as well. And so the final step is to factor out the orange box, which is just P of S0, A0, S1, A1, right? So that's the thing I boxed up in orange, times then those two terms involving the derivatives. Times the payoff. Okay. And I think, right, where I guess this term goes there, and this term goes there. Okay. And so this is just equal to, well, and if you look at the reinforced algorithm, right, that we wrote down, this is just equal to sum over, all the state action sequences times the probability of the gradient update. Right. Because I guess I'm running out of colors. But this is a gradient update, and that's just right equal to this thing. Okay. So what this shows is that even though on each iteration the direction of the gradient updates is random, the expected value of how you update the parameters is exactly equal to the derivative of your objective, of your expected total payoff, right? So we started saying that this formula is your expected total payoff. So let's figure out what's the derivative of your expected total payoff. And we found that the derivative of your expected total payoff, the derivative of the thing you want to maximize, is equal to the expected value of your gradient update. And so this proves that on average, if you have a very small learning rate, you end up averaging over many steps, right? But on average, the updates that reinforce is taking on every iteration is exactly in the direction of the derivative of the expected total payoff that you're trying to maximize. Okay, that makes sense? Any questions about this? Yeah. Is this independent of the choice of logistic function? This is true for any form of a stochastic policy where the definition is that pi theta of S0 A0 has to be the chance of taking that action in that state, but this could be any function you want. It could be a softmax, it could be a logistic function of many, many different complicated features. It could be, it has to be a it has to be a differentiable function. And actually, one of the reasons we shifted to stochastic policies was because previously you just had two actions. It's either left or right, right? And so you can't define a derivative over a discontinuous function, like either left or right. But now we have a probability that shifts slowly between what's the probability to go left versus go right. And by making this a continuous function of theta, you can then take derivatives imply gradient descent. But it doesn't be a logistic function. Yeah, go ahead.
Something maybe not quite related to that, but could one also just have an expert helicopter rider, like ride helicopter, and then just fit a logistic regression on this or her action, and how well would it work?
Sure. So another way to train a helicopter controller is to use supervised learning, where you have a human expert train, so you can also actually have a human pilot demonstrate in this state, take this action, right? And then use supervised learning to just learn directly a mapping from the state to the action. I think this, I don't know, this might be okay for low-speed helicopter flight. I don't think it works super well. I bet you could do this and not crash a helicopter, but to get the best results, I wouldn't use this approach. Yeah. It turns out for some of the maneuvers, we actually fly better than human pilots as well. Yeah, not all, but yeah, cool. All right. Oh, and so for other types of policies, let's see. All right. So direct policy search also works if you have continuous value actions and you don't want to discretize the action. So maybe here's a simple example. Let's say A is a real number, such as the magnitude of the force you apply to accelerating left or right? So rather than discretizing your inverted pendulum, you want to output a continuous number of how hard you accelerate to the left or right. Or for a self-driving car, maybe theta is the steering angle, which is a real value number. So a simple policy would be A equals, theta transpose S, and then plus Gaussian noise. And if just for the purpose of training, you're willing to pretend that your policy is to apply the action theta transpose S and then add a little bit of Gaussian noise to it, then the whole framework for reinforce, for this type of gradient descent also will also work. And then I guess if you're actually implementing this, you probably turn off the Gaussian noise. Right? There are little tricks like that as well. So let's see, some pros and cons of, so when should you use direct policy search and when should you use value iteration or a value function based type of approach? So it turns out there's one setting, actually there are two settings where direct policy search works much better. One is if you have a POM-DP, PO in this case stands for partially observable. And that's if, for example, for the inverted pendulum, that's the pole angle phi, you have the car, and this is your position x. And we've been saying that the state space is x dot phi dot, right? But let's say that you have sensors on this inverted pendulum that allow you to measure only the position and only the angle of the inverted pendulum. So you might have an angle sensor, down here, and you might have a position sensor for your inverted pendulum, but maybe you don't know the velocity and you don't know the angular velocity, right? So this is an example of a partially observable Markov decision process because, and what this means is that on every step, you do not get to see the whole state because you don't have enough sensors to tell you exactly what is the state of the entire system. Okay? So in a partially observable MDP, at each step, you get a partial and potentially noisy measurement of the state, right? And then have to take actions. Have to choose an action A. Using these partial and potentially noisy measurements, right? Which is maybe you only observe the position and the angle, but your sensors aren't even totally accurate. So you get a slightly noisy, estimate of the position. You get a slightly noisy estimate of the angle, but you just have to choose an action based on your noisy estimates of just two of the four state variables. Right? It turns out that there's been a lot of academic literature trying to generalize value function-based approaches to POM-DPs, and there are very complicated algorithms in the literature on trying to apply value function-based approaches to POM-DPs. But those algorithms, despite their very high level of complexity, are not widely in production, right? But if you use the direct policy search algorithm, then there's actually very little problem. Oh, let me just write this down. So let's say the observation is on every time step you observe y equals x phi plus noise, right? So you just don't know what is the state. And in a POM-DP, you cannot approximate the value function, or even if you knew what was v star, right? You can't compute pi star because, I mean, maybe you know what is pi star best. Let's say you can compute v star and pi star. But if you don't know what the state is, you can't apply pi star to the state. So how do you choose an action? If you're using direct policy search, then here's one thing you could do, which is you can say that pi of, given an observation, the chance of going to the right, given your current observation, is equal to 1 over 1 plus e to negative theta transpose y, where I guess y can be 1, right, x plus noise, phi plus noise, right? But so that's x plus noise, phi plus noise, right? And so you could reinforce using just the observations you have to try to stochastically, try to randomly choose an action, and nothing in the framework we talked about prevents this algorithm from working. And so direct policy search just works very naturally, even if you have only partial observations of the state. And more generally, instead of plugging in the direct observations, this can be any set of features. Right? I'll just make a side comment for those of you that know what common filters are. Don't worry if you don't. But one common way of using direct policy search would be to use some estimate, such as a common filter or probabilistic graph model or something, to use your historical estimates. Don't just look at your one set of measurements now, but look at all your historical measurements. And then there are algorithms such as something called a common filter that lets you estimate whatever is the current state, the full state vector. You can plug that full state vector estimate into the features you use to choose an action. That's a common design paradigm. If you don't know what a common filter is, don't worry about it. Maybe take one of Stephen Boy's classes or something. I don't know. Yeah, right. But that's one common paradigm where you could use your partial observations, estimate the full state, and plug that as the features into direct policy search. Okay. So that's one setting where direct policy search works. Just applies in a way that value function approximation is very difficult to even get to apply. Now, one last thing is one last consideration for should you apply a policy search algorithm or a value function approximation algorithm. Oh, it turns out the reinforced algorithm is actually very inefficient, as in you end up, when you look at research papers on the reinforced algorithm, it's not unusual for people to run the reinforced algorithm for like 1 million iterations or 10 million iterations. So you just have to train. It turns out the gradient estimates for the reinforced algorithm, even though the expected value is right, is actually very noisy. And so if you train the reinforced algorithm, you end up just running it for a very, very, very long time, right? It does work, but it's a pretty inefficient algorithm. So that's one disadvantage of the reinforced algorithm, is that the gradient estimates on expectation are exactly what you want it to be, but there's a lot of variance in the gradient, so you have to run it for a long time with a very small learning rate. But one other reason to use direct policy search is kind of ask yourself, do you think pi star is simpler, or is v star simpler, right? And so here's what I mean. There are, in robotics, there's sometimes what we call low-level control tasks. And one way to think of low-level control tasks is flying a helicopter. Hovering a helicopter is an example of a low-level control task. And one way to informally think of low-level control tasks is, can a really skilled human, holding a joystick, control this thing, making seat of the pants decisions, right? So those are kind of almost instinctual in a tiny fraction of a second, almost by feel, you could control the thing. Those are tend to be low-level control tasks. Those are seat of the pants, holding a joystick, a skilled person could balance the inverted pendulum or, steer a helicopter. Those are low-level control tasks. In contrast, playing chess is not a low-level control task. Because for the most part, to be a very good chess player is not really a seat of the pants, take a look, make a decision in 0.1 seconds, right? You kind of have to think multiple steps ahead. And in low-level control tasks, there's usually some control policy that is quite simple. A very simple function, mapping from the states to the actions, that's pretty good. And so that allows you to specify a relatively simple class of functions of pi star, and direct policy search would be relatively promising for tasks like those. Whereas in contrast, if you want to play chess or play Go or do these things where you have multiple steps of reasoning, I think that if you're driving a car on a straight road, that's a low-level control task. You just look at the road and you just turn the steering wheel a little bit to stay on the road. So that's a low-level control task. But if you are planning how to, overtake this car and avoid that other car while there's a pedestrian and the bicyclist along the way, then that's less of a low-level control task, and that requires more multi-step reasoning, right? I guess depending on how aggressive a driver you are, right? Driving on a highway, may require more or less multi-step reasoning where you want to, overtake this car before the trucker comes in this lane. So that type of thing is more multi-step reasoning. And approaches like that tend to be difficult for a very simple, like a linear function to be a good policy. And for those things in playing chess, playing Go, playing checkers, a value function approximation approach may be more promising. Okay. Cool. So any questions about the, and so again, for autonomous helicopter flight, actually, my first attempts for flying helicopters were actually direct policy search, because flying a helicopter is actually seat of the pants things. But then when you try to fly more complex maneuvers, then you end up using something maybe closer to value function approximation methods if you want to fly a very complicated maneuver. Right? So the video you saw just now of a helicopter flying upside down, the algorithm implemented on, for that particular video, that was a direct policy search algorithm. Right? Not exactly this one, a little bit different, but that was a direct policy search algorithm. But if you want a helicopter to fly a very complicated maneuver, then you need something maybe closer to value function approximation algorithm. And there is exciting research on how to blend direct policy search approaches together with value function approximation approaches. So actually, AlphaGo, one of the reasons AlphaGo worked was, Go plane program, right, by DeepMind. It was a blend of ideas from both of these types of literature, which enabled it to scale to a much bigger system to play Go in a clearly very, very impressive level. All right, any questions about this? All right, so just final application examples. Reinforcement learning today is making strong, let's see, so there's a lot of work on reinforcement learning for game playing, checkers, chess, Go. That is exciting. Reinforcement learning today is used in a growing number of robotics applications. I think for controlling a lot of robots, there is I don't know, if you go to robotics conferences, if you look at some of the projects being done by some of the very large companies that make very large machines, right? I have many friends in multiple, large companies making large machines that are increasingly using reinforcement learning to control them. There is fascinating work using reinforcement learning for optimizing entire factory deployments. There's academic research work, still in research work as far as I know, actually maybe starting to be deployed on using reinforcement learning to build chatbots. And actually on using reinforcement learning to build a AI-based guidance counselor, for example, right, where the actions you take are what you say to students, and then the reward is, do you manage to help a student navigate their coursework or navigate their career? there is, and it's also starting to be applied to healthcare, where one of the keys of reinforcement learning is this a sequential decision-making process, right? Where do you have to take a sequence of decisions that may affect your reward over time? And I think, in healthcare, there is work on medical planning, where the goal is not to, send you to get a blood test and then we're done, right? In complicated medical procedures, we might send you to get a blood test, then based on the outcome of the blood test, we might send you to get a biopsy or not, or we might ask you to take a drug and then come back in 2 weeks. But it's this very complicated sequential decision-making process for treatment of complicated healthcare conditions. And so there's fascinating work on trying to apply reinforcement learning to this sort of multi-step reasoning, where it's not about, we'll send you for a treatment and then never see you again for the rest of your life. It's about, here's the first thing you do, then come back. Let's see what state you get to after taking this blood test, or let's see what state you get to after trying a drug, and then coming back in a week to see what has happened to your symptoms. But I think that these are all sectors where reinforcement learning is making inroads, or even actually stock trading. Okay, maybe not the most inspiring one, but one of my friends on the East Coast was and just actually, if you or your parents invest in mutual funds, this may be being used to buy and sell shares for them today, depending on what bank they're investing in. I know what bank is doing this, but I won't say it out loud. If you want to buy or sell, say 1 million shares of stock, a very large volume of stock, you may not want to do it in a very public way, because that will affect the price of the shares, right? So if everyone knows that a very large investor is about to buy 1 million shares or buy 10 million shares or whatever, that will cause the price to increase, and this disadvantages the person wanting to buy shares. But so there's been very interesting work on using reinforcement learning to decide how to sequence out how to buy the stock in small lots in these trading markets called dark pools. You can Google it if you're curious. Actually, don't bother. To try to buy a very large lot of shares or sell a very large lot of shares without affecting the market price too much, because the way you affect the market price always breaks against, it is always against you. It's always bad, right? So this work like that as well. So anyway, I think many applications. I personally think that one of the most exciting areas for reinforcement learning will be robotics, but we'll see what happens over the next few years, right? Okay. All right. So let's see. We're just 5 more minutes. And just to wrap up, I think I don't know, we've gone through quite a lot of stuff, I guess, from supervised learning to learning theory and advice for applying learning algorithms to unsupervised learning, all the, K-means, PCA, EM mixture of Gaussians, factor analysis, independent component analysis, to most recently reinforcement learning with the value function approaches, fitted value iteration, policy search. So feels like you've seen a lot of learning algorithms. Go ahead. How does reinforcement learning compare to adversarial learning? I think of those as a pretty distinct literatures. Yeah. So I think, and again, actually, I know a lot of non-publicly known facts about the machine learning world, but one of the things that I actually happen to know is that some of the ideas from adversarial learning, so can you tweak a picture by, very little bit, by tweaking a bunch of pixel values that are not visible to human eye, that fools the learning algorithm into thinking that this picture is actually a cat when it's clearly not a cat or whatever. So I actually know that there are attackers out in the world today using techniques like that to attack, websites, to try to fool some of the websites that I'm pretty sure you guys use fool their anti-spam, anti-fraud, anti-undermining democracy types of algorithms into making poor decisions. So it's an exciting time to be machine learning, right? That we get to fight battles like these. Okay, and I think with really, I think that with the things you guys have learned in machine learning, I think all of you are now very knowledgeable, right? I think all of you are experts in all the ideas of core machine learning. And I hope that I think when you look around the world, there's so many worthwhile projects you could do with machine learning, and the number of you that know these techniques is so small that I hope that you take these skills. And some of you will go, build businesses and make a lot of money. That's great. Some of you will take these ideas and help drive basic research at Stanford or at other institutions. I think that's fantastic. But I think whatever you're doing, the number of worthwhile projects on the planet is so large, and the number of you that actually know how to use these techniques is so small that I hope that you take these skills you're learning from this class and go and do something meaningful, go and do something that helps other people. I think we've seen in Silicon Valley that there are a lot of ways, to build very valuable businesses, and some of you do that, and that's great, but I hope that you do it in a way that helps other people. I think over the past few years, we've seen I think that in Silicon Valley, maybe 10 years ago, the contract we had with society was that people would trust us with their data, and then we'll use their data to help them. But I think in the past year, that contract feels like it has been broken, and the world's faith in Silicon Valley has been shaken up. But I think that places even more pressure on all of us, on all of you, to make sure that the work you go out into the world to do is work that actually is respectful of individuals, respectful of individuals' privacy, is transparent, open, and that ultimately is helping drive forward humanity, or helping people, helping drive forward basic research, or building products that actually help people rather than exploit their foibles for profit, but to their own harm. So I hope that all of you will take your superpowers that you now have and go out to do meaningful work. And let's see. And I think, and lastly, just on a personal note, want to thank all of you on behalf of the TAs, the whole teaching team, and myself. Want to thank all of you for your hard work. Sometimes they go over the homework problems, look at project milestones, and go, "Wow, they actually got that problem. I thought that was really hard." Or look at project milestones, and go, "Hey, that's really cool. Look forward to seeing your final project results at the final poster session." So I know that all of you have worked really hard. And if you didn't, don't tell me. But I think almost all of you have. But I want to make sure you know that I think it wasn't that long ago that I was a student, working late at night on homework problems, and I know that many of you have been doing that for the homeworks, for studying for the midterm, for work on your final term projects. So want to make sure I'm very grateful for the hard work you put into this class, and I hope that your hard-earned skills will also reward you very well in the future, and also help you do work that you find is meaningful. So thank you very much.